Okay, to wrap up this chapter, we're going to do some trigonometric application problems, and we're going to start by talking about harmonic motion. And harmonic motion just simply refers to the motion that an object makes as it is kind of rotating or oscillating or just basically moving in any type of wave motion. And since it's kind of moving like a wave, it would make sense to use sine or cosine since those graphs have that kind of wave-like behavior. And whether or not we use sine or cosine really just depends on whether or not our object is starting out at its maximum, at its high point, or somewhere at the equilibrium line. In looking at the general forms of sine and cosine, we're going to see that they look pretty similar to our general standard forms for these trigonometric functions. Um, D is still going to be our displacement or the distance of a point from the equilibrium at a certain time t. The absolute value of A is still our amplitude, or representing that maximum displacement. So if I would draw it in this problem here, the absolute value of A, which talks about that amplitude or the maximum displacement from that equilibrium. And 2 pi over W is still our period, which is the time it takes to complete one cycle. And the only difference really here is that W over 2 pi, this represents our frequency. W over 2 pi is our frequency, not just W itself. So take a moment, pause the video, and write these down if you need to, but let's dive right into this first problem. Okay, so a buoy oscillates in simple harmonic motion as waves go past. At a given time, it is noted that the buoy moves a total of 3.5 feet from its low point to its high point, and that it returns to its high point every 10 seconds. Write an equation that describes the motion of the buoy as if it is at its high point at time t is equal to 0. Then we're going to use that equation to find the first time the buoy passes the point of equilibrium. Well, if the buoy is starting out at its high point, that means we want to be using the cosine graph here. So I'm going to say d is equal to a times cosine of wt. Well, we know that this entire distance from the high point to its low point is 3.5. So we can then say that our amplitude here has to be half of that distance. So half of 3.5, which is 7/2. So our amplitude is going to be 7/4. We're also told that it returns to its high point every 10 seconds. That is to say, its period is 10 seconds. And so we can set that equal to pi over 5 times t. So if we solve for t here, we can say that, I'm sorry, not that pi over 5t. Our period is going to be 2 pi over w, I apologize. So if our period is equal to 10 seconds, and that's equal to 2 pi over w, we can say that w is equal to 2 pi over 10, or pi over 5. So we have everything now that we need to write our equation. We can say d is equal to 7/4, there's our amplitude, cosine of pi over 5 times t. Now that we have our equation, let's use this equation to find the first time the buoy passes the point of equilibrium. In other words, when d is equal to 0. So all we're going to do is set this equal to 0. And in the next chapter, we're going to do a lot of solving trigonometric equations, but for now, this is actually pretty easy to do. We're going to divide both sides by 7/4, and we just need to ask ourselves, what is the first angle such that the cosine of that angle is equal to 0? Well, theta is equal to pi over 2. That's when cosine is equal to 0. And so we're going to set what theta was, which is pi over 5 t. Set that equal to pi over 2. So t is equal to pi over 2 times 5 over pi, and that just comes out to 5/2 seconds. Okay, so there would be an example of a harmonic motion problem. Okay, all right, now let's talk about bearings. And this is probably something you'll see a little bit more often in this chapter. But a bearing describes the measure of the positive acute angle a path or line of sight makes with a fixed north or south line. So to kind of describe this, let me just draw a vertical line. Do that again. The vertical line. Here's my horizontal line. And I'm just going to label the directions here. North, east, south, west. A couple mnemonic devices that you might be familiar with. Never eat shredded wheat, or never eat soggy waffles. Seems to be the one more popular with my students. But I'm a fan of never eat shredded wheat. That one actually rhymes. So what is a bearing describing? It is describing the direction that you would be moving or heading towards from the vertical line as you move towards the horizontal. So for example, suppose you said something like south 75 degrees due east. So that's the notation, south 75 degrees due east. What that means is from the south vertical line, we're going to be moving 75 degrees towards the horizontal. So whenever we're doing our bearings, we're always going to be saying the vertical moving towards the horizontal. So from the south, which would be down here at the south, 75 degrees due east, we'd be moving 75 degrees in this direction. And this is different from what we've done so far in this chapter. This is really the only time we draw angles that are not placed from in standard position from the positive x-axis. We're starting from the vertical and we're going towards the horizontal. So south 75 degrees due east. Okay. So what about something like, let me change this color here, north 40 degrees due west. Take a moment and think about what north 40 degrees due west would look like. So we can sketch something that looks like we have north and we're going to go 40 degrees due west, something like this. Okay. All right. So hopefully this gives you a sense of what bearings look like. Now let's actually try some problems where we actually have to apply our understanding of bearings. Okay. So let's take a moment, read through this first question here. So we have an airplane, it's 120 miles north, 45 miles west of the airport. And the pilot wants to go back to the airport or fly to the airport. What bearing should be taken? Well, in this problem here, it makes sense that the airport would be down here because the pilot, or the airplane, I should say, is northwest of the airport. So I should say it's 120 miles north and it's 45 miles west. Okay, so I can kind of draw this vertical here. This would be north, south, east, west. Okay, so it's 45 miles west. That means that airplane, the plane I should label, is over here. And that airplane wants to head back or head to the airport. So what bearing should be taken? Think about where that bearing would be. Since a bearing involves the angle from the vertical, I have to draw a vertical here from the airplane. And the bearing from that the plane wants to take to the airport would be this angle here. This would be angle theta, right? Because it is the angle from the vertical heading towards the horizontal. So as that plane clearly needs to go southeast. So from the south going east, what is that angle? So pause and think about this for a second. How could I figure out that angle? And what we can do is actually apply our understanding of alternate interior angles to say that these two lines are parallel to each other. This angle here that I have labeled as theta is congruent to this angle theta. And I can then say that the tangent of this angle theta is opposite over adjacent, or 45 over 120. And theta then would be approximately equal to the arc tangent of 45 over 120. And this is something that you'd have to punch into your calculator, but this comes out to be approximately, so I should say it's not approximately that, it's exactly equal to that, but approximately equal to 20.556 degrees. So that's my angle theta here. That means that's the angle theta here. So we can then say the pilot, should fly at a bearing of south 20.556 degrees due east. Okay? All right. Let's try this next problem now. This next problem involves a sailboat and it's leaving a pier at 8 knots. So just to be clear, a knot represents a nautical mile per hour. It is a rate. It is not a unit for distance, but a rate. So we have a pier down here and it's heading west. So let me just kind of see if I can do this. It's heading west. Okay. And let's see, we can do that. Sailboat leaves the pier, heads west at 8 knots. So the boat is going to head west at 8 knots. So I'll just write this here. Okay, 8 knots. After 15 minutes, the sailboat tacks, which means it stops, and it's going to change course to north 16 degrees due west. So we can take this one here. Let me just copy that. Go that here. So north 16 degrees due west. In other words, it's going to go 16 degrees from the vertical, and that's probably way larger than 16 degrees, but you get the idea. Something like that. And it's going to go in that direction at 10 knots at 12 minutes. So the boat is now here. What we're concerned with is finding the bearing from the pier to the boat after 12 minutes on that course. Okay, so to be very clear here, oops, let's delete that. Let's copy that again and put that right here. I'm concerned with finding this following bearing. I want to find this bearing here, which I'll call theta. Okay? So from the pier to the boat, I want to find this bearing here. And we know a few things. We know that this angle is 16 degrees. We know that this, we don't have the distance here, but we can figure out this distance. We know that distance is equal to rate times time. And from this distance here, the rate is equal to 8 nautical miles per hour. And if you're traveling for 15 minutes, that would be 1/4. That looks like too much like a negative. That would be 1/4 of an hour, which, if we simplify here, this comes out to be 2 nautical miles. So this here, if we're traveling 8 knots at 15 minutes, this would be 2 nautical miles. Well, what about this length here? Well, distance equal rate times time. This is 10 nautical miles per hour times 1. You're told that it's 12 minutes, which is 1/5 of an hour. So if we simplify that, this comes out to 2 nautical miles. So this is 2 nautical miles. Okay? So if we know that's 2 nautical miles, this is 2 nautical miles, and this is our right angle here. Now, do we have everything we need to figure out this angle theta? Well, hopefully you identified that these two sides are congruent with one another, making this an isosceles triangle. Further, if we know that this angle here is 16, that this angle here has got to be 90 degrees plus 16, so this is 106 degrees. Well, this doesn't actually require any trigonometry at all. We can say that 180 minus 106 is going to be the sum of these two angles here. That's equal to 74. And then 74 degrees divided by 2 is going to give us 37 degrees, which is this angle down here. Well, what would theta then be? Theta would then be the complement of 37, or 53 degrees. So we can then say the bearing from the pier to the boat is north 53 degrees due west. This would be 53 degrees here. And the bearing is north 53 degrees due west. All right? Okay, so hopefully this helps understand some of our applications of trigonometry with things like harmonic motion and bearings.